Hello everyone. In this video we will do some examples for invertibility of linear vector field using determinant. The equation is given us two matrices, 2 by 2 and 3 by 3, with some entries as an unknown in terms of unknown k. And the question asks for what values of k the vector field defined by these matrices are invertible. Well, just recall the first thing is that while checking invertibility using the original condition that we had, maps a non-zero vector to zero, would be very difficult in these cases to be checked. Instead, what we have is this very nice statement that a linear vector field is invertible if and only if the determinant of the coefficient matrix is non-zero. And these examples show the strength of this statement. Okay, so it means that we have to start with the determinant of the matrix. Here we have 2 by 2 matrix. The determinant is straightforward. You just multiply the main diagonal minus off diagonal entries, and then this is k squared minus k. Okay, and we want to see when it is zero, when it is non-zero. So I will go with the zero part. So that means that k minus 1 must be equal to 0. This means either k is 0 or k is 1. So what we showed that determinant of A is 0 only for values of k being 0 and 1. And other than that, the determinant must be non-zero. So that means that the vector field is invertible for all k's which are not 0 and not 1. Anything else you put there, it will define a vector field which is invertible. Let's do the same thing for this 3 by 3. So again, I will start with the determinant of the coefficient matrix or defining matrix of the linear vector field. We're expanding along the first row. So here I have k in the intersection, so this is k, determinant of the remaining 141 k squared, minus, then go to the second one, and this will give you this piece here, which will be 0 times determinant. So here's an important point. Since it is 0, whatever the determinant of remaining part is, it's going to be multiplied by 0. So I don't need to know that because anything multiplied by 0 is going to be 0. The same story goes for the third component. And as you see, this is going to be 0 times determinant of some remaining part, but those guys are going to be at the end zero sum end. So that means that the only remaining part is this piece here times the determinant, and that is k squared minus 4. And I don't need to expand this because I'm letting that to be equal to 0. Determinant of A being equal to 0 means that k times k squared minus 4 is equal to 0. This means either k is 0 or k squared minus 4 is equal to 0. From there, you get either k is 2 or k is negative 2. So I have three values which make determinant 0. Other than that, determinant must be non-zero. So determinant of A is not equal to 0 for all k's which are not 0, negative 2, and 2. Well, as a result, the vector field defined, the linear vector field defined by this guy is invertible for all the values of k which are not one of these three, either not 0, not -2, not 2, then anything else you choose, that will give us a matrix with non-zero determinant. So as a result, a linear vector field which is invertible.